speaker is María Inés de Frutos Fernández, and she's going to talk about formalizing the divided power envelope. Thanks.
Hi, thanks very much for the introduction, and thanks to the organizers for inviting me to present this work. Everything that I will discuss today is joint work with Antoine Samerlois. We are formalizing something called the divided power envelope. I expect that most of you have never heard this before, and that's completely fine. I'm not going to assume that you know what this is. And I'm going to split the talk into three parts. So first, I will give you some motivation as to why we decided to formalize this particular mathematical object. And the motivation for us comes from number theory or from arithmetic geometry. Then, in the second part of the talk, I will describe the basic theory of divided powers. So I will start with the definitions, if you have never seen this before, and like basic examples, basic constructions around divided powers. And then finally, in the last part of the talk, I want to comment on how to formalize two universal constructions. So the first one is something called the universal divided power algebra, and the second one is this divided power envelope. Okay, so starting slow with the motivation, I first want to start by introducing several fields that are interesting for number theories. So we all know the real numbers. The real numbers can be constructed by taking the rational numbers, considering the Euclidean absolute value on the rational numbers, and taking the completions. But it so happens that the Euclidean absolute value is not the only absolute value that you can consider on the rational numbers. In fact, there's infinitely many more, because for each prime number p, you get an interesting absolute value on the rational numbers. And for this absolute value, the idea is that p is small, so something that is very divisible by p is small in the p-adic topology. So some examples here, if you look at, you consider the integer 2 to the 10 times 3 to the 8 times 5 to the 4, and you want to look, you want to compute the three-adic absolute value. You have to look at what is the power of 3 that appears in the decomposition. In this case, it's 3 to the 8, so the three-adic absolute value is 3 to the minus 8. So this number is relatively big for the usual absolute value, but it is small for the three-adic absolute value. And then we can extend this definition to fractions. So for that, we have to divide absolute values of the numerator and the denominator. So for example, the three-adic absolute value of 1 over 3 to the 4 is 3 to the 4. So yeah, I haven't proven this to you, but like the function that you get in this way is, again, an absolute value on the rational numbers. So we can again do the same thing. We take the rationals, we complete with respect to this p-adic absolute value, and we get a new field, QP. So this is known as the field of p-adic numbers. So this is by construction analog to the real numbers. Now, next question is, now that we have an analog to the real numbers, can we also get a p-adic analog to the complex numbers? And since the complex numbers are obtained from the real numbers by taking the algebraic closure, that's the natural thing to try, right? So we just take the algebraic closure of QP, and we wonder whether that is a good analog for the complex numbers. But not quite, because by construction, this field that we obtain is algebraically closed. So this is good. This is one of the properties that we want. And it's not trivial to show this, but it is possible to show that the p-adic absolute value admits a unique extension to the algebraic closure of QP. And this is something that I formalize in Lean in my second formalization project. So this is something that we have available. What fails for this to be a good analog of C is that the algebraic closure of QP is not complete with respect to this extension of the p-adic absolute value. So what we do is we take one extra step. So now we take the completion of the algebraic closure of QP with respect to the p-adic absolute value, and we call that CP. So we are going to say that that is the p-adic analog of the complex numbers, because now by construction we got something that is complete, and we can prove that it is algebraically closed. So this is a better analog for the complex numbers. Okay, so this is one of the things that I wanted to introduce from number theory. The second thing that I want to introduce are Galois representations. So we start by defining the absolute Galois group of QP. So this Galois group is defined as taking the automorphisms of QP alt, of the algebraic closure of QP, that fix QP pointwise. So this has a group structure, it's an infinite group, and we can give it a topology so that it becomes a topological group. And then we can define a p-adic Galois representation as a continuous group homomorphism from this group GQP to the general linear group over V, where V is some finite dimensional QP vector space. So in particular, notice that we have the same prime on both the domain and the codomain. So p-adic Galois representations are one of the objects of study for number theories, and it's very hard to understand like what kind of properties these representations have. So there are like several techniques that have been developed for this. And for example, one question is whether some of these Galois representations come from geometry. Like for example, if you have a nice variety defined over QP, and you look at the étale cohomology groups of this variety, this is a source of examples of Galois representations. But if someone gives you a Galois representation, like how do you know if it's a representation of this form? Okay, so Fontaine defines several rings to try to understand Galois representations better. One of these rings is called B-crease, and this is one of the situations in which this ring is important. So we've already mentioned the étale cohomology of a variety, but the étale cohomology is not necessarily the only cohomology theory that you want to study. You might also want to understand the rank cohomology or the crystalline cohomology. And ideally, you want to understand how all of these cohomology theories are related to each other. So in particular, we have this comparison theorem for crystalline cohomology. So this says that if we have a nice variety over some p-adic field K, and we have some nice model for this variety over the integers of this field K, well then the result is that after tensoring with this ring B-crease, which I have not defined yet, we get that the crystalline cohomology groups become isomorphic to the étale cohomology groups, and also that this isomorphism preserves some interesting arithmetic information. So it respects the Galois axioms that we have on both sides, and also respects the Frobenius axiom. So this is one place where this ring B-crease shows up. Yes.
Can I just ask you, does B-crease depend on K?
Yes, yeah. But yeah, I'm not going to use the definition of B-crease really in this talk. This is just to motivate. Yeah. Okay, so yeah, he defined this ring B-crease. It's not the only ring that he defined. In fact, he defined several so-called Fontaine period rings. And these rings can be used to detect whether some p-adic Galois representations have certain interesting properties. So I've already mentioned B-crease, and in that case, representation is crystalline if it's B admissible for this ring B-crease. To check if it's B admissible, what you have to do is you have to compute some certain invariant that depends on the ring and the Galois representation. But then let me also give you some examples that are a bit easier. So the first example of period ring will be just taking the algebraic closure of QP. And in that case, the representation being admissible for this ring is equivalent to the Galois axiom of GQP on the space V, factoring through a finite quotient. And then the next example, we take V to be the p-adic complex numbers. Then we have something similar. In this case, V is CP admissible if and only if the axiom of the inertia group on P factors through a finite quotient. So yeah, our motivation to study the divided power envelope is that it's going to show up in the construction of this ring B-crease. The definition of B-crease is very complicated. I'm going to show it to you in the next slide, but I'm not going to focus in any of the details at all. So why am I showing you the definition? Two reasons. One reason is to show you that this is somewhere where the divided power envelope appears. The other reason is to show that definitions in number theory, in algebraic number theory, can be extremely complicated, but also that we have like basically all of the ingredients that we need to formalize this definition already in Lean, and many of them already in MATLAB. Okay, so yeah, this is the definition of B-crease. These are all of the steps that you need to take. So I'm not going to explain this carefully. And this is the last time that big crease is going to appear in the talk. So don't worry if you have never seen this before, you don't need it for the rest of the talk. Okay? But just quickly, we start with the p-adic complex numbers, which, remember, already constructing this is not trivial. There's some theorems that you have to prove, but that's something that we already have in Lean. Then you have to take a pre-tilt, which again, it's something relatively complicated, but which is available in Mathlib. Then you have to take something called a ring of bit vectors. You have to define some homomorphism from the ring you obtained to the p-adic complex numbers. And then at that point, we have to take something called the divided power envelope of this ring A-inf with respect to the kernel of this morphism that we have defined. So the talk today is about whatever this divided power envelope is and how to formalize this in Lean. Yes?
Is this for like the Farks Fontaine curve?
Is this really Fontaine?
Yeah, I guess it can be related, but like, let's not talk about that. Yeah. Okay. So once we have the divided power envelope, we still have to take a few more steps, but the remaining steps again are things that we can do in Lean. So we can take the p-adic completion, we can invert p, and then we can invert this other element t. So really, the only obstruction right now to having this very complicated definition in Mathlib or in Lean is constructing this divided power envelope. Okay, so this is our motivation for working on this project. Now, as I promised, now we forget about this very complicated definition and we are going back to the beginning of divided powers. So this is the overview of our project. We first, I will first introduce the definition of divided power structure. So for that, we fix a ring A. All of the rings today are going to be assumed to be commutative rings. And we fix an ideal in the ring. A divided power structure on the ideal I is going to be a family of maps from the ideal to itself, indexed by the natural numbers. And we ask that this family satisfies the same properties as the family x to the n over n factorial. Now, this is in quotes for now because I didn't make this precise, but I will make this precise later. Yes?
So, just a question, because here you're using natural numbers which are greater or equal to 1. And I remember from reading David Ledger's paper that working with naturals at least 1 is problematic.
We will get to that in a second. We will see that in the formalization we don't restrict to greater than equal to 1. But for now, like in the informal definition, you usually see it like this. Okay, so in the first part of the talk, I'm going to show you the precise definition of divided powers, and I'm going to develop some of the basic theory of this, like morphisms, sub-ideals, things like that, and some examples. And then once we have all of the basic theory, remember, what we want to do is we want to construct this divided power envelope, which is some kind of universal construction. But this relies on a previous universal construction, which is the universal divided power algebra. So that's something that you can attach to every A module M. For every A module M, you can construct a ring, an ideal, and divided powers on this ideal, such that some universal property that I will show you later is satisfied. And then once we have that, we can use it to define some other universal construction, the divided power envelope. So this is attached to the data of a divided power algebra, so ring A, ideal I, divided powers gamma, and then some ideal J in an A algebra B. Attached to this data, we can construct another divided power algebra, which is a B algebra. And again, this is going to satisfy some kind of universal property relating this to the divided powers on I. Okay. So the history of divided powers started in the 1950s. And in fact, the original motivation had nothing to do with number theory. So these were, divided powers were first introduced by Carl Tang. And he was working in algebraic topology. He was trying to understand the homology of Eilenberg-MacLane spaces. And he introduces this construction of divided powers. However, many of the main proofs, including the construction of the universal divided power algebra, were done by Groby in the 1960s. However, the divided power envelope comes later. That was developed by Berthelot in the 1970s. So in the late 1960s, Rothendijk introduced crystalline cohomology, and then the theory of crystalline cohomology was developed by Berthelot over the following decade. And while developing this theory, he defined this divided power envelope. And then in 2022, I met Antoine Samerloire at a conference in ICERM. So it was one of the first Lean for the Curious Mathematician conferences. And we decided that we were going to collaborate together on constructing this divided power envelope in Lean. So to start, our first reference was a book by Berthelot and August on crystalline cohomology. And in this book, you can find a chapter on how to construct the divided power envelope. However, we quickly realized that that didn't have enough details because Berthelot doesn't give you the full construction of the universal divided power algebra in that chapter. There is an appendix in this book where he gives you like a sketch of the proof of how to construct it, but again, this is only a sketch, so it's not nearly enough detail to then take this and put it into Lean. So we quickly realized that we actually had to go back to the original source and look at the papers by Robbie. So for that, there's one paper from 1965, which has the construction of the divided power algebra, and this relies on a previous paper from 1963 about polynomial laws. And we'll come back later in the talk to some of the issues that we encountered when we were trying to formalize that paper. Okay, but before getting to that, let's just look at the basic theory. So now let me make precise the definition of divided powers. Now, we let I be an ideal in the commutative ring A. A divided power structure on I is a collection of maps from the ideal to A, indexed by the natural numbers. So now I am allowing 0 in particular, satisfying these properties. So the first property is that for every element in the ideal, gamma naught of x is equal to 1. Then gamma 1 of x has to be equal to x. And we also ask that for every positive n, gamma n of x is in the ideal I. So that's how we recover this first imprecise version that told you that gamma n goes from the ideal to the ideal. And then we have 4 more properties that tell you how these behave with respect to different operations. So if you take the divided power gamma n of a sum of elements in the ideal, that's going to be given by this formula on the right. And then you also get formulas for scalar multiplication, for multiplication of divided powers, and for compositions of divided powers. Where do all of these formulas come from? Well, these formulas come from the properties that the family x to the n over n factorial satisfies. So you can check that all of the properties in the previous slide are satisfied by this family, and this is not hard to check. So the first 2 are very easy, right? Like x to the 0 over 0 factorial is equal to 1, x to the 1 over 1 factorial is equal to x. Now, to get the property for the sum, you just expand x plus y to the n, right? And then you cancel the n factorial that you have in the numerator with the 1 in the denominator, and then you rearrange the sum a little bit. So that gives you this formula that we have here, right? This will be the formula for the sum. And then you can do the same thing for the other formulas. So basically, all of the formulas on this slide are an abstraction of what happens for the family x to the n over n factorial. Okay. And this is the code in Lean. So I'll focus, I'm not going to read everything to you, but I want to explain a few of the differences with the informal definition. The first difference is that in the informal definition, I am asking that A is a commutative ring. Here I'm asking that A is a commutative semi-ring. So it's fine to generalize things to generalize this theory to semi-rings, but on the other hand, we don't know what the theory should be for non-commutative rings or semi-rings, so we don't relax the commutativity hypothesis. The second big difference is that in the slide here, I said that this is a collection of maps from the ideal to A. However, in the formalization, the way that we do this is we have a family of maps from A to A, and then we have one extra hypothesis that if x is not in the ideal, then the value is just 0. So we don't care about what happens outside the ideal, but since terms in Lean only have a unique type, We don't want this to be the ideal I, because then we will have to apply like a lot of coercions and things get more complicated. It's nicer if we just define this map in order ring, and then we have this extra condition. Yeah, and the next few lines are just the formalization in line of the properties. So yeah, what else I should say? So this anti-diagonal n is the way that we have in line of writing down the family of tuples ij such that I plus j is equal to n. So we use that. We use that here in the formula for the sum. And then something else is we define this uniform bell. So if we go back to the informal definition, we see that here we have this kind of combinatorial looking number. And it's not clear from this formula, from this expression, that this is an integer. But in fact, this is always an integer, and that's something that we have formalized. And it has a combinatorial interpretation. So you can interpret this as the number of partitions of a set with n times n elements into m subsets of size 10. Okay, and then from this definition, we can prove that we have the equality n factorial times gamma n of a is equal to a to the n. So this, again, should emphasize the analogy with the family x to the n over n factorial. Okay. So the first thing that we formalized after we had the definition were some examples of ideas in which we have divided powers. So the first example is if we take the ring A to be any Q algebra and we take any ideal in A, we always have a unique divided power structure on the ideal, and that is the family given by x to the n over n factorial. So in a Q algebra, you will always be able to divide by n factorial, and we can prove that the properties force this to be the only divided power structure that you can have. The second example, which is more interesting, is if we have the p-adic integers as the ring, and we consider the ideal generated by p, this again has a unique divided power structure. And to check that, what we have to prove is that p to the n over n factorial belongs to the ideal generated by p. So to check this, we have to check, we have to compute the p-adic absolute value of this number, and that tells us the information that this number is divisible by p as a p-adic integer. Okay, and the last source of like easy examples is it has to do with nilpotent ideals. So we have an ideal such that I to the n is equal to 0 and n minus 1 factorial is invertible in the ring A. In that case, again, we have a unique divided power structure, which is x to the n over n factorial. In the formalization, we use the same construction here and here, actually. And three special cases of these constructions are if we have a ring of characteristic p and an ideal such that I to the p is equal to 0. More generally, if we have a ring where the prime p is nilpotent, it's not necessarily equal to the characteristic, but it is nilpotent, then that's still the case that if I to the p is equal to 0, this will be the unique divided power structure. And then the simplest example is in any characteristic, if I square is equal to 0, then, well, 2 minus 1 factorial is 1, so that's invertible everywhere, so you will always have divided power structures. Okay. So these are some examples, but then you can also develop some basic theory for these divided powers. So if you have divided powers on an ideal I of A and an ideal K of B, you can define a morphism between these divided power structures. And this is going to be a ring homomorphism from A to B, such that the image of the ideal I is contained in J, and such that the map is compatible with the divided power structures, meaning that this quality is satisfied for every n and for every element in the ideal I. So we define this notion of DP morphism in Line, and we prove some properties like composition of DP morphisms is a DP morphism, and study the kernel and the image of DP morphisms and so on. We also define sub-divided power ideals. So that is just a sub-ideal J of the ideal I, such that for every positive natural number and every element in J, gamma n of x is also in J. And then there are several constructions that are interesting. So in particular, what happens when you take intersections or sums of ideals? So the first thing is you take the intersection of J with the ideal I, where you have divided powers. This is a sub-DP ideal of I, if and only if we have a divided power structure on the ideal generated by I on the quotient green, such that the quotient map is a divided power morphism. So this is something that we formalize in general and that we will need for the construction of the universal divided power algebra. This is one of the properties that we need. Another interesting construction is if we have two ideals with divided power structures that agree on the intersection, then we can prove that there is a unique divided power structure on the sum that extends both the divided power structures on I and J. And we actually proved that sub-divided power ideals of I form a complete lattice. I'm not going to give you the details of all of this. I'm going to focus on this construction here, so the construction of divided powers of a sum of ideals, because I think this is interesting from the formalization point of view. So yeah, there is a unique divided power structure on the sum that extends both of these divided power structures. For that divided power structure, we get that the identity map is a divided power morphism from I to I plus J, and similarly for J. And there are two ways, at least, that you could use to formalize this. So the first implementation, so this is the first thing that we did because it requires a lot less background, so it was easier to do with what was already present in Mathlib, is just provide the formula explicitly. So if we have an element in the ideal I plus J, we know that we can decompose it as the sum of an element X in I plus an element Y in J. And then we use two things. So we use that we have a formula for what the divided power of a sum has to be. And then we use that we want this gamma I plus J to be compatible with the other two divided power structures. And this tells us that this is the formula that has to be true for the value of the divided powers in the sum. However, there are two problems with this approach. The first problem is that we have to check that this is well defined, right? Because if there are in general, there are more than one way to express an element in this form. So we have to check that if we choose two different decompositions, we still get the same value for the divided powers. So we formalized that. So it was annoying, but it was doable. And then, this is an explicit summation, and checking all of the proofs of all of the properties got very annoying. A lot of reordering of sums and things like that. So it wasn't very nice to formalize. So we wanted to do another approach, which was more elegant from the mathematical point of view. But the problem is that required a lot more background, which was not available in Mathlib, and that's why we didn't do it at the beginning, but we decided to do it in the end. And the idea for this is attached to the ring A, we can construct something called the exponential model, which I will define in the next slide. And whenever we have divided powers on an ideal I, we get a map from this I to the exponential model. So we can deduce the divided power structure on the ideal I plus J by saying that the map that we get from I plus J to the exponential map has to be the unique linear map that extends these two linear maps. Okay, so two things were missing in order to be able to do this in Lean. The first thing is this linear algebra resolves that tells you there's going to be a unique linear map from the sum. This was missing, but this was not very hard to add. The serious issue was how to construct this exponential model. So now I will tell you what that is and what we had to formalize to get there. Okay. So we consider the ring of power series in one variable over the ring A. And we are going to say that a power series F is of exponential type if it satisfies two properties. So the first property is f of 0 is equal to 1. The second property is it satisfies this functional equation. So if you substitute x0 plus x1, so these are variables, you substitute them into the power series f, this will be the same as f of x0 times f of x1. Okay, and then the exponential module of A is the subset of the power series ring consisting of power series of exponential type. And it's perhaps not immediately clear how this is a model, but this becomes a model where the addition is given by multiplication of power series, and the external law is given by rescaling power series.
What do you mean by rescaling?
Yes, like taking the multiplying the variable by some constant.
Oh, rescaling
Yeah.
on the height.
Yeah. Yeah. Okay. So we, if we want to use this approach, we need to formalize this exponential module in Lean, right? But yeah, the next two things are that, so supposing that we have this exponential module, then for every divided power ideal I on A, you can consider the power series given by this formula. So just the coefficients are going to be gamma and A. And this power series that you obtain in this way, this is of exponential type, so it belongs to the exponential module. And that gives us a map from the ideal to the exponential module just by sending the element A to this exponential power series attached to A. And this is a morphism of A models. Okay. Now, the problem is this functional equation that I wrote here, this was not possible to do in Lean because we had no way of like evaluating f at the variable x0 plus x1 or of substituting this like sum of variables into the power series. So what did we have to add to make this possible? Well, a bunch of things. So first, let's now suppose that A is a topological ring, B is an A algebra, and sigma is a set of indeterminates. Now we can define the ring A of multivariate power series over A, where the variables are indexed by this set sigma. This ring is naturally endowed with the product topology. So we formalize this, we make it into a scope instance. We don't make it a global instance because there may be other topologies that you want to consider in this ring. Next thing is we needed to formalize linear topologies on rings and modules. Then once we have that, we can start talking about evaluation of power series at a family of elements in an A algebra B. However, this is not always possible, right? So if you have a multivariate polynomial and you want to evaluate this polynomial as at a family of elements, you can always do that because evaluating a polynomial, you just need to take a finite sum, right? But here we are dealing with power series, so in principle, these are infinite sums, so it's not clear that they don't always make sense, right? So we formalize that this is possible to do under certain topological conditions, certain conditions of the topology on B, which in particular has to be a linear topology, and also on these values where we want to evaluate. And then as a special case of evaluation of power series, we get a substitution of multivariate power series. Again, this isn't always possible, but it is possible under certain conditions. So to give you an idea, if the set of variables is finite, then we just need to check that the constant coefficient of each of these elements, Bs, is nilpotent. In that case, we can substitute. Okay, so this was a lot of extra work in order to get a more beautiful definition of divided powers on the sum of ideals. But it's also work that we are hoping is going to be very useful for other people that are formalizing in Lean. So we decided to take the time to do it. Everything that I have told you so far is completely finished. We wrote it up for a paper that will appear in ITP 2025. And this is about 8,000 lines of code in Lean. More than half of this is already in MATLAB. The rest we are still working on getting into MATLAB. Okay. Now, for the rest of the talk, I want to explain how we deal with these universal constructions. So this is still ongoing work, so I'll tell you which parts are done and which parts we are still working on. But let's start with the construction of the universal divided power algebra. So yeah, I will make precise what this is now. So we have an A module M. The claim is that there exists a divided power algebra. So remember, this is the data of a ring, an ideal, and a family that behaves like x to the n over n factorial. And then this comes together with an A linear map from the module to this ring that we are constructing that has this universal property that if we take any other A algebra B and an ideal J in B with divided powers, together with a map from the module M to the ideal J, then there is a unique divided power morphism from this universal divided power algebra to this ideal J in B that splits this map, so such that this composition is equal to the original map. Okay. So we want to formalize this in. As I said at the beginning, the details are all in papers of Robbie from the 1960s, so that's the proof that we are following. And Robbie starts by providing an explicit construction of what this ring has to be, what the ideal has to be, and then proving that it has divided powers. So getting the ring and getting the ideal is easy. To define the ring, Robbie defines this by generators and relations. So generators, I'm using Robbie's notation here, so you get a generator x to the n for each x in the module M and its natural number n. And then you impose these three kinds of relations for like scalar multiplication, multiplication of like divided power, multiplication of generators, and taking generator associated to a sum. So yeah, we encode this in Lean. So we define a relation over the multivariate polynomial ring with coefficients in the ring R, and so R is what I'm calling A in the informal test, and variables indexed by n times m. Yeah, so the first condition here is just for convenience, basically, and then these other three conditions are these three relations that we have in the previous slide. So we define the ring just by taking the quotient by these relations. Okay. Now, getting the ideal is also easy. So the ideal is going to be generated by the generators of the form xn, where x is in M and n is greater than or equal to 1. We also get some more structures on these divided universal divided power algebras. So if these generators xn have degree n, then the relations are homogeneous. And that means that the universal algebra gamma m is a graded algebra. The degree 0 part of this algebra is isomorphic to the ring A, and the degree 1 part is isomorphic to M. And then the augmentation ideal is, as I said, generated by x to the n, where n greater than or equal to 1. So getting the ring is easy, getting the ideal is easy. The hard part comes at showing that this actually comes with a divided power structure. So we want to show that it has divided powers, and also that the divided power structure that you get is unique. Uniqueness is easy. Okay, so if there is a divided power structure on this ideal, it has to be unique, and this is because every element set in this ideal can be expressed as a finite sum of this form, which means that using the properties in the definition of divided powers, we know what the formula will have to be in terms of this. So yeah, like we are only using the definition. We are not using anything else here. But this will tell us that the formula for gamma n of z has to be given by this product. So if there is a divided power structure, it is unique. But the hard question is there a divided power structure on this ideal? And this is in fact so much harder than there is a mistake in the proof. So Robbie proposed a proof of this in a paper of 1965. So this paper is where he constructs the universal divided power algebra. And in case you are curious, the problem is in lemma 8 of this paper. And I'm just copying the mistake in the proof. So this comes in this line here. So Robbie is saying that we know that there exists an R isomorphism of algebras from this universal algebra tensor with R to this other universal algebra. Well, we don't know this because in fact this is false. Yeah, so he's actually given a reference here, and the reference that he's giving is a previous paper by Robbie, so something that he wrote. And if you go to the reference and you try to find this result, you find the corrected version of this result. So what he actually proved in 1963 is that this thing on the left is isomorphic to the universal the divided power algebra of M tensor R, which is in general not the same as this universal divided power algebra. So this was scary when we found out, because this means that we could not fix the proof of lemma 8. Lemma 8 is false. Lemma 8 is used later in the proof. So this is also the reference that everyone uses for the construction of the universal divided power algebra. So until we figured out how to fix this, we were worried that something was very wrong with the theory. But luckily, that's not the case. We can fix the proof. So we have to ignore this lemma 8, which doesn't work at all, and we have to ignore part of the original proof of Robbie. But somehow, all of the right ideas were already present in this paper. So if you go a bit further down the paper, there's this other lemma 12, and he proves this only for modules over the integers, but you can generalize the ideas to make it work for modules over other rings. So that way we got a different proof, and the proof that we got is simpler than the original proof. So I'm going to try to explain quickly what the idea of the new proof is. Okay, so remember, we have M is an A module, and what we are trying to compute is this thing here. We are trying to compute divided powers on the universal divided power algebra of M. We don't know how to do that. So what we are going to do is we are going to construct some related universal divided power algebras in which we do know how to construct the DP structure, and then somehow we are going to use that to recover the divided power structure on this ring. Okay, so what do we need? We need to start with R being an integral and faithful set algebra that comes equipped with a morphism, a surjective morphism to the ring A that we started with. In our implementation, we just take R to be polynomials over the integers with coefficients indexed by the ring. Okay, now we let F be the field of fractions of this ring R, and we let L be the free R module that has a basis given by the generated family for the module M. Okay, so we have first this diagram of rings, right? So here, this ring R is included into its fraction ring. Yeah.
What do you mean by faithful? Faithful is the other one. You mean something that Z embeds inside this thing? So what does faithful mean?
Faithful as a module. So you don't want. So you want that if something kills all of the elements, it has to be 0. Yeah. Yeah. So yeah. Yeah. So we have this inclusion of R into its fraction field F. We have the surjection to the ring A, and here I'm just taking the equality from A to A. Now starting from this, we construct a diagram of modules. So I'm going to tensor everything with L. So again, here I have an inclusion, here I have a surjection, and here we can combine the relations to recover the module M. And now we can apply this divided power algebra functor to get this map at the level of universal divided power algebras. Okay. So now the sketch of the proof is as follows, and everything here has been formalized except for these two things that I'm marking with an asterisk. This is still sorry, and I will say a bit more not much more because I don't have a lot of time, but I'll say a bit more about that. Basically, we do this in 4 steps. So we want to get here to the right to define divided power structure. Here, we don't know how to do that, but if we start on the left, this one here, this is a Q algebra. And I said at the beginning that the first example of divided powers is that if you have any ideal in a Q algebra, you know that x to the n over n factorial is the unique divided power structure. So we know what the divided powers are in this ring. The next step is recovering divided power structures in this other ring. So in order to do that, we have to show that this is this algebra is free. This means that this is a subalgebra of the one on the left. And because of that, we can recover the divided power structure on the ideal on the right using the one on the left. Yeah, so the part that is missing is the freeness statement. Now, again, I said at the beginning of the talk that we know how divided powers interact with quotients. So to pass from here to here, we just have to take the quotient of the divided power structure. And then for the last step, so to get what we actually want, we actually have to prove something. We have to prove that the kernel of this morphism is stable under divided powers. By that, I mean that if we look at the kernel of this map, then the kernel here is generated by the divided powers of elements in the kernel here. And using that property, we can again pass to the quotient and obtain the desired divided power structure on the universal divided power. Okay, so yeah, there are 2 things missing, and for that, we need to formalize polynomial laws. This is something that we always knew that we were going to need to use some results about polynomial laws, but because of this, using a different proof here, we actually have to formalize more than we realized at the beginning. So polynomial laws are studied in this paper of Roby from 1963. This is a very long paper, so the full paper is 137 pages. We only need the first part of the paper. The first part is 76 pages. We don't need everything, but we need a lot of it. So that's what we are working on now. We have some of it formalized already, but there's still some work that we have to do. Yeah, maybe I will skip the details about polynomial laws, but this is something that we have to formalize now in order to fill these last 2 stories in the proof of the universal divided power algebra. But yeah, in case you are curious, the definition of polynomial law is already in MATLAB, but not much else. That we have the definition, but then we have some results locally, but not in MATLAB. And there's a universe issue here that Mario was saying before that maybe we don't run into universe issues, but we did. Okay. Yeah, these are the theorems that we will need to finish. But my title of the talk talks about the divided power envelope, so let me say something about it very quickly. Now, the divided power envelope is determined by this universal property. So we start with divided powers on an ideal I. We have an A algebra B with an ideal J. And then the claim is that we can construct a divided power algebra dB gamma J prime omega. So for every divided power algebra CK delta, that's a B algebra, and that admits a dP morphism from A. The claim is that there is a unique divided power morphism from this divided power envelope to this divided power algebra, making this diagram commute. So in the formalization, what we do is we have this definition here of is dP envelope. So is dP envelope is encoding this diagram here, so it's encoding the universal property that has to be satisfied. Then we provide a candidate for being the divided power envelope. So this is actually going to be an explicit quotient of the divided power algebra. So I'm omitting the details here, but this is something that we have. And this is the reason why we first need to construct the universal divided power algebra, is because we want to recover the divided power envelope, and that is constructed as a quotient of this. And yeah, then we have to prove a theorem that this explicit divided power envelope actually satisfies the right universal property. So yeah, this is almost done, but there's still a bit of work to do here. And yeah, these are all of the references that we follow. So first, Berthelot and Berthelot-August tell the story of the divided power envelope. This is the paper. This is the paper with the mistake in the proof, and this is the paper, the very long paper that we are trying to formalize now. Yeah, that's everything. Thank you very much for your attention.
So in the universal divided power algebra construction, so in the uniqueness part, there is kind of a formula. So what goes wrong if you try to prove that this formula works?
There's a formula. Wait, sorry. I went too far, I guess.
Yes. Yeah, that one. So can't you just take this formula as the definition and then suffer through the computation?
I guess possibly, but again, you have issues of like whether this is well defined and yeah.
So it's a worse version of the problem that you wanted to avoid earlier.
Yes, probably. Yeah. I mean, somehow like there's, I don't know, there's like an infinite number of variables, an infinite number of relations. Like it's very, I don't think you can just try to compute everything. Yeah.
Another question is, so you've got this very long paper to formalize, and aren't you tempted to just, do what Kevin would be doing, try to do other people to do your job and just set up a blueprint and ask for just crowdfund this 76 pages long formalization?
Yeah, well, I don't know. So somehow the story with this formalization project has been that every time we think that we are close to finishing, we discover that there's like 30 more pages that we have to formalize. So like somehow maybe that's part of the reason that we thought that we could do this alone from the beginning instead of like trying to set it as a big collaborative project. Yeah.
That's funny because it's exactly how this lean blueprint stuff started. So in the beginning, it was the Perfectoid Spaces project, so with Kevin and Johan. And Kevin was constantly telling us, oh yeah, we're almost done, and then discovering 30 more pages of preliminaries that he forgot about, or never knew about. And then when I wanted to start the next project, I thought we need to avoid that and build technology to approve.
Yeah, but I mean, we have to formalize still like these. So really what's missing is these 3 theorems from the paper from 1963. But the proof of this requires to develop a lot of the theory in like chapters 1 and 2 of the paper. And we are doing that. We are also running into some technical issues with Lean, like partly because we make the definition for commutative semi-rings, but then there are some of the things that we would like to use that in principle could be formalized for commutative semi-rings, but right now are only massive for commutative rings, and that's giving us some trouble. Also, like there's this universe issue that I glossed over, right? Like in this definition here, you need to make sure that all of these algebras have the same universe as the ring R that you started, but then we need to generalize that to like every other possible universe. That we have a version of that, but first we need to generalize it to commutative semi-rings, so we need to avoid somehow like using these results in math that are only stated for rings. And also we are waiting on some work of Joel Ryu that he's preparing now that will allow us to make this in a nicer way. So, yeah. But yeah, so there are some things that are slowing us right now in like continue to formalize this paper, but they will get resolved at some point. Yes.
So, so you're more or less reduced to the case of free modules, right?
Mm-hmm.
And so, if M is a free R module, then your gamma R of M is just the sum of you take the k-fold tensor power and you take the symmetric group invariance in that.
In the case of free modules, we just embed it into the free Q algebra and we recover the divided power structure from there.
I mean, you shouldn't need to reduce the Q algebra, right? I mean, if you've got a basis for M, then you've got a basis for the symmetric part of the k-fold tensor power of M.
But my guess is that will be harder to formalize than just like inheriting from the Q algebra.
Okay.
Yeah. Like working with explicit basis is not always the easiest way to work in.
So, in my mind, the two big applications of divided powers are firstly crystalline cohomology, and secondly this ring B Chris. And do you need all this machinery just for those two applications, or have you just fallen into this got to do it the Maslin way trap?
I mean, we need this for the definition of decrease, right?
You need all of this machinery.
Yes, because we need it to construct the divided power envelope.
Okay, so that's exactly,
Yeah, so we need all of this, yeah. For example, we didn't technically need to like develop the topology of multivariate power series rings, but because we could have used this like other like more explicit version of the definition, but like so there are some things that we did like in a nicer way to like put into MATLAB, but like yeah, like this we need the full construction of the divided power envelope.
I actually see the application you didn't mention, so there are not only those applications. I see very good applications, realizations of infinite dimensional algebras, Lie algebras, so it goes very well.
Okay.
There was a question at the back there.
So I was wondering when you said that lots of MATLAB lemmas should be generalized to semi-rings instead. Do you know of any examples where you cannot work with commutative rings but need commutative semi-rings? So this is just generalization from the fundamental.
Well, I don't know if it's for the fun of it. It's like if that we were also wondering like if this is like really the right definition to pass to commutative semi-rings instead of just sticking with commutative rings as done in the literature. But somehow, like if everything works for semi-rings, we should state it for semi-rings. The problem that we have right now, for example, is like the way that this is stated is like something has to be true for like every semi-ring that is an algebra over R. Right, so when you're trying to prove results for this, so for example, I say that we have these like two fan and this is compat that currently only work for rings. So like you get into trouble because you have to translate to like to rings somehow, which is possible technically, but like not really what you want to do. I mean, it's possible in the sense that in MATLAB, like there's like an algebra dot semi-ring to ring that tells you that if you have an algebra over a commutative ring, this is again, an algebra over a ring, this is a ring, if you know that it is a semi-ring. But then you end up with like diamonds, and like it's clearly not the right way to do it.
The concept of an ideal is not even the right. You're putting divided bound structures on ideals, right? And for
Yes.
semi-rings, an ideal is kind of a weird. But the point of ideals of rings is they're the kernels of surjections. And for semi-rings, that's not true anymore. You know, surjections and ideals are just two completely different things. So it's sort of.
Yeah.
You have to be careful. And the point of divided powers is to do exponential and logarithm and translate multiplication into addition. And you're doing exponential, but for crystalline cohomology you'll be doing logarithm as well, and that's got minus signs everywhere.
So maybe in some cases you need to restrict to comb rings, but that's fine, right?
I mean, at the end of the day you'll need to restrict to rings, and the question is where do you stop? And you'll have to make some pragmatic decision at some point.
Yeah.
Because it's not entirely clear to me that anyone's going to be ever using the theory for semi-rings.
Yeah.
Just a comment. I reviewed the first PR and I said to Antoine, well, the definition works even for semi-ring. You don't need commutativity to state the definition. And he told me, Serre told me that this is wrong for if it's not commutative. So apparently someone knows something about this stuff. Not in the case of not a commutative ring. So.
Well, I would say that ideals are wrong.
Yeah, I don't know, but yeah.
Kevin, did you notice this morning during Flores talks there were modules of our non-negative real numbers everywhere?
Yeah.
They can sell it semi-ring, so
Is there one last question there?
Yeah, you said in a lot of your slides you were saying there was a unique power structure. Is there always a canonical power structure? About a power structure? When there isn't? Is that a meaningful question?
Do you mean like for every ideal in every ring? Or like what do you mean?
I guess I mean if there is some divided power structure, is one of them somehow more canonical than the rest? Okay, could this be a type class?
no.
So, I mean, there are cases like, for example, for Q-algebras where you only get one, like if there is, well, in Q-algebras there's always one, but there are other examples where you could put different divided power structures. Yeah.
Okay, it's that, Maria. Thanks very much.